In this lesson, we will discuss counting principles. There are a lot of real-world examples where a lot of choices are being made, and it's good to be able to count the total number of possibilities or outcomes from these choices. Depending on the example, this can be quite difficult to do. Counting principles refers to the formulas that you can use to speed up this process and make it a little bit more easy to solve. To motivate this idea, let's look at example 1. Two friends go out to dinner and order a pizza to share. They each decide to let the other choose a topping. So we have one friend who wants either pepperoni or sausage, and the other's going to choose from mushrooms, banana peppers, or olives. So here we have choices being made. How many different combinations of toppings are there? So here we have choices being made. How many possible outcomes are there in this problem? To solve this without using a counting principle, you can just list out every single possibility. And I want to take that approach first. So we have two friends, and they are going out to eat. And here, this is the first friend, and they're choosing between pepperoni or sausage. I'm going to use an arrow diagram to indicate their choices. Going this way, we can go with either pepperoni, or this way, we can go with sausage. Now, once that choice is made, the second friend can say, all right, well, depending on these choices, I'm going to go with one of these three things. If the first person chooses pepperoni, then from here you can say, oh, well, we'll either have pepperoni and mushrooms, pepperoni and banana peppers, or pepperoni and olives. But if the first person chose sausage, it would be these three choices, but down here. So I'm going to double them. It could be sausage and mushrooms, which sounds great, sausage and banana peppers, or sausage and olives. If you want to know the total number of different combinations, we can just count all of them over here at this very last step. There's 3 here, there are 3 here. The total possible number of combinations is 6. Another approach you can use here that might be faster is to note that, well, if you have these choices, these 3, and there's 2 choices being here, you can just take the product of 2 and 3. I like thinking of it like this. There's a choice being made for the first category and a choice being made for the second category. There are 2 possibilities in the first and 3 possibilities in the second. If you multiply those 2 together, you do get 6. And that makes sense in our picture. Here there's 3 choices, but then we double it. We multiply it by 2 to get 6. And that's what this fact says up here. If there are n possible choices from one group and m possible choices from the second, then the total number of 2-item choices is the product of these 2 numbers. As a formula, you can say that is equal to n multiplied by m. And if you can see that right at the beginning of this problem, you can avoid doing all this and just say, it's 2 times 3, and that is 6. This formula is especially nice if there are a lot of choices being made. I mean, for this problem, it could have been maybe the first person was choosing between, 10 different toppings, and the second person was choosing between 8 different toppings. So, this is like, well, what if this was the scenario? How many different possible combinations of toppings are there? It's simply going to be 10 times 8, which is 80. Why does this process make sense? Well, first, you'd have not 2 arrows, but 10 arrows. And then for each of those now 10 arrows, there's 8 possible choices. So you're taking 8 and counting it a total of 10 times. That is precisely what 10 times 8 is equal to. So this counting principle is quite powerful in that it can speed up the process very quickly. But it has its limitations too, because it only works for 2 groups, because we're talking about a 2-item choice. What if there were 3 groups or 3 choices were being made, or 4 or 5? Can we generalize this principle? The answer is yes, and we will look at that on the next slide. At the top, I have stated the generalized version of this counting principle. The number of ways in which a series of groups of items can be counted is found by multiplying the number of ways each individual item can be counted. So what this means is, if you have groups, let's say n M, and a third one, P, and that's the number of choices you can make from each group, then the total number of ways that the items can be counted is N times M times P. And this works for any number of groups. It could work for 40 groups. It's hard to draw that in symbols because there's not enough letters, but you could say, maybe N sub 1, N sub 2, N sub 3, all the way until you get to the 40th group. So here these ellipses mean we're just going to keep counting until we get to 40. If you have this many groups, and this is the number of items in each group, then the total number of ways that the items can be counted is simply the product of all of these groups multiplied together until you get to the last one. Let's see why that works in example 2. Example 2 is the same as example 1, except a third friend is going to join and put a topping on the pizza. So we got the first friend choosing between the pepperoni and sausage, the other mushrooms, banana peppers, and olives, but then Dave shows up and wants to add his own topping, and that is the choice between pineapple and anchovies. I think I'll first solve this by drawing a diagram just to see what that looks like. I don't think it'll be too complicated. So, we have our two friends, the first and the second, and then Dave shows up, friend number 3. And it starts the same exact way. So the first person says, okay, either pepperoni or sausage. The second friend was like, I want either mushrooms, banana peppers, or olives. But now we have 6 choices because it was 2 times 3. Dave has 2 possible choices in this third category, meaning for each one of these spots, we can branch off into 2 directions. So with the choice of first, let's say pepperoni and mushrooms, there are 2 choices up here, pineapple or anchovies. And I see there might be some confusion, so I'm going to use the letter N to represent pineapple. So the choices for that first part are, we could have either pineapple or anchovies. So there's one of the possible combinations, pepperoni, mushrooms, and pineapple, or pepperoni, mushrooms, and anchovies. That's true for all the remaining ones. So we could have pineapple and anchovies. We could have pineapple and anchovies. And then that is copied down here. How many possible outcomes are there? Well, there were already 6 from here. And now what you're doing is multiplying that by 2. I mean, we had 6 choices. There's 2 arrows going off of each of those choices. That is 6 multiplied by 2. So the answer to this is we have 3 groups. There were 2 choices for the first, 3 for the second, and then going from this step to this step, you're multiplying each of those by 2. So you multiply by 2 again. That's 2 times 3 is 6. 6 times 2 is 12. So there's a total of 12 choices. So that's what this principle means. If you have 3 categories, you can simply multiply the number of choices in each to get the total number of choices. Let's apply this generalized counting principle in examples 3 and 4. Starting with example 3, a restaurant offers 5 appetizers and 12 main courses. In how many ways can a person order a 2-course meal? So let's start there. There are 2 groups, one for the appetizers and then one for the main courses. And within each of those groups, there were 5 appetizers and 12 main courses. Therefore, the total number of 2-course meals is 5 times 12, and that is 60. So for this first question here is 60. Okay, there's a couple more parts. Next, it asks, what if there are 3 choices for dessert? So not a 2-course meal, but we're assuming this person orders a 3-course meal. They must choose something from each category. Well, this time, let's see. There are appetizers, the main course, and then dessert. And if we're choosing one from each category, that's 5 for the first, that is 12 for the second, and then 3 for dessert. So here, the product of these three numbers is 3 times 60. That is 180 possible combinations. So for this question, the answer is 180. Okay, there's a final part here. What if we assume the person orders a main course, so they're picking something from here, and they're also going to have a dessert, but they may or may not have an appetizer. So how many different possible meals could they have? So for this one, there's still 3 choices. So I'm going to draw, let's see, we have 1, 2, 3. The part I'm pretty certain about is for the main course, there's 12 choices, and they're still having 3 possible choices for dessert. But here we're saying they may get an appetizer or they may not. If you say may not, that means there's a 6th possibility here that they don't get anything. So that is 6 that I'll put in this spot. So possible meals that they could have had include the fact that maybe they did not have an appetizer. So I increased this 5 to 6. Now, if I take the product of those 3, 6 times 12 is 72, and 72 times 3 is 216. So I'll highlight the fact that, okay, for this last question, where they don't necessarily get an appetizer, 216 possible things could happen when they go out to eat their meal. Moving on to our last example, example 4, says you are taking a multiple choice quiz with 4 questions on it. And each question has 5 possible choices. If you leave no question unanswered, in how many ways can you answer these questions? If you quickly look at this, you might say, okay, we got 4, we got 5. I know this. The answer is simply 4 times 5, and that is 20, and I'm done, right? No. This is not correct. This is no good. Why does that not work? I mean, what's the actual approach to solve this using the counting principles we have? Well, how many categories are there? If you look at this previous problem, there was 3 categories when we got to the last 2 parts because we were choosing for appetizers, main courses, and desserts. How many categories are in this problem? Here, the number 4 is referring to the number of categories because you're answering 4 separate questions. So if I start by drawing out each individual group, there are 4 groups or 4 categories, however you'd like to phrase it. And then for each of these groups, there's a total of 5 possible choices. So here in each group, we're putting, there's 5 choices for the first, 5 choices for the second, the third, and the fourth. This is the approach you should take for answering this problem. So this is no good. Again, I'll just put this in a box and say, no, that this is wrong. But what is correct is to say, it's 5 choices for the first, times 5 for the second, times 5 for the third, and then 5 for the fourth. And once all those choices for each question has been made, if we take the product of these numbers, 5 times 5 is 25. So this is 25 and this is 25, and 25 times 25 is 625. So that is the total number of ways that you can answer 4 questions if each has 5 possible choices. So in a sense, the process we did here is a lot like saying 4 friends go out to have a pizza together, and each of them is going to choose between 5 toppings that goes on the same pizza. So a lot of these questions will read in a very similar way, but look out for the numbers that appear within the problem. Sometimes they refer to the number of different ways you can make choices, but sometimes the numbers refer to the actual categories themselves.